In this presentation, I introduce two optimization techniques, linear programming and the traveling salesperson problem. You can also think of these optimization techniques as prescriptive analytics in that they prescribe a solution for an organization to implement. There are three major types of analytics. Descriptive analytics, which typically are tables and visuals, and you've already learned how to prepare these using the dplyr package in R and ggplot. The second type are explanatory or predictive analytics, which essentially answer the question, can we explain why Y occurs? And if we do that with sufficient precision, then we can predict why. The third type, prescriptive, which is the feature of this presentation, asks the question, what should be done? The first optimization technique I will discuss is linear programming. This is a mathematical technique that was developed in 1948 for determining how to optimally allocate a set of resources subject to a linear objective function and linear constraints. So the first word linear in linear programming comes from the notion that there are linear constraints and a linear objective function. Linear programming is an entry point to the general field of mathematical programming on optimization. There are many other tools in the optimization area that build on the principles of linear programming that were established when it was first introduced. For linear programming, the word programming means an algorithm, a set of steps for solving a problem to give a particular solution. Specification of a linear program requires four elements. First, the set of variables to be determined. Second, the linear objective function to be minimized or maximized. Then we specify each of the linear constraints in the form of a less than or greater than statement. And finally, we have to specify any non-negative results. The problem is common in business. It requires taking two or more input sources to produce two or more output sources. In this problem, we have two suppliers of fuel that are the components of fuel A and fuel B. The blended fuels produce pollutants, and regulations require that these be removed. The cost of removing these pollutants is $3.5 per tonne for fuel A and $4 per tonne for fuel B. The company's goal is to minimise the cost of removing pollutants. Furthermore, fuel A is a blend of 50% of fuel from supplier 1 and 50% of fuel from supplier 2, and fuel B is a 75% of the fuel from each of these suppliers, respectively. We can now specify the linear programming problem. We have two unknowns, the number of tonnes of fuel A to produce and the number of tonnes of fuel B to produce. We want to minimize the cost of removing the pollutants, and we have two constraints. We must buy at least 200 tonnes from supplier 1 and 300 tonnes from supplier 2. As the blending problem has only two variables, x and y, to be determined, we can create a graph to show the feasible region and the possible solution. The first step is to graph each of the constraints. These are the red lines. And notice that we graph them for equality. Anything above the intersection of the two red lines is the feasible region. Any value in this area is a solution to the problem. But we're interested in minimizing the objective function. The green line is a mapping of the objective function for the solution when x equals 800 and y equals 700. And you can see this lies in the feasible region. If we move this line parallel to itself to the left and look for the last point where it touches the feasible region, then that will give us the minimum. In this case, the minimum will be when x equals 300 and y equals 200. Let's examine the same blending problem with a different minimization function, in this case 3.5x plus 6.0y. We create a similar green line in this case and move it parallel to itself, and you'll see here the minimum touches where we have a value of x for 600 and a value of y for 350. So as you change the objective function, you can get a minimum solution that is different. In every case, the minimum must lie on the edge of the feasible region. Of course, a graphical solution is only useful when you have two variables. You want a more general approach. So here is the R code for solving a linear programming problem, in this case, the blending problem. You'll need to install the library LP Solver API. Then you can specify the nature of the linear programming problem. So I've defined LP here, and I do a make.lp to start with 0 constraints and two variables, the two variables being the x and y. Next, we set the objective function. We tell it that the data is going to be stored in LP, and the 3.5 and 4 are the coefficients of the objective function. We then specify the two supply constraints. We've now specified the model, and we can check this specification by printing LP. And you'll notice the console output, which is in grey, indicates that we have two variables to solve. In this case, the computer has called them C1 and C2. We see the minimize function appearing first, and then the two constraints, and then some other information that doesn't particularly concern us at this stage. And then finally, we can solve the problem. So we write solve in brackets LP. We've solved the problem, but at this stage, we don't know the results. So the first thing to do is to retrieve the objective function and print it out. We can use getObjective to get the results, and then with the paste function, we can put together a short report. In this case, we see the pollution costs are $1,850. We can use getVariables to retrieve the number of tonnes produced for A, fuel, and B, fuel. As you can see, we produce 300 and 200 of each of these respectively, and we can add the two together to ensure that we have 500 tonnes. And finally, in the report, we show supplier 1 produces 200 tonnes, which is what is required, and we buy 300 tonnes from supplier 2. The final part of the solution that is interesting is called the dual solution, which provides some shadow prices. And we retrieve these, and you'll see that I've added a paste function to tell us something about these shadow prices. First of all, we ignore the first variable, the 1.0, and look at the second two variables, the 2.5 and the 4.5. Again, I use the paste function to interpret the values for you. So you'll see that it states that requiring 1 more tonne from supplier A will increase the cost by 2.5. The second statement says that requiring 1 less tonne from supplier B will decrease the cost by 4.5. These shadow prices enable us to make decisions about where we would get extra supplies from. Should we focus on supplier? Should we use supplier 1 or supplier 2 if we need additional fuel? Alternatively, we could increase the supply from one and reduce the supply from another so that we still get 500 tonnes of fuel, but in the process, reduce our total pollution costs. It's now time to consolidate what you have learnt about the blending problem and linear programming. First of all, review the optimization slides that are available via a link on the syllabus. Then run the code for the blending problem, which is in the slides, a line at a time. You can do this by positioning the cursor on the first line and then select the code using either Command Enter or Control Enter, depending upon the operating system that you use. I suggest that you inspect the output for each line of code as you progress so that you understand how to formulate and execute a linear programming problem. Here's a quick exercise to demonstrate the usefulness of shadow prices. You might recall from the previous results that if we increase by 1 tonne the amount from supplier A, the cost will go up by $2.5. And if we decrease the amount from supplier B by 1 tonne, it will decrease by $4.5. So if we rerun the problem with these new constraints, then we should see a decrease in the objective function of $2. That is, 2.5 minus 4.5 is minus 2. And we subtract this from 1,850 to get 1,848. Check your results. This exercise will enable you to further your knowledge of how to specify a linear programming problem for a blending issue. In this case, we have a power plant that has to generate 2,000 megawatts for the next hour, subject to certain EPA requirements that the emission of pollutants is below 900 kilograms per hour. The plant has several options. Obviously, it wants to minimize its cost while meeting the requirement for generating electricity. It can burn high or low sulfur fuel with or without stack filters, or it can input power. In each case, there are certain pollutants produced and a cost per megawatt hour for that particular source of energy. Step is to identify the variables to be computed. In this case, we have 5. High sulfur fuel, low sulfur fuel, high sulfur fuel with stack filters, low sulfur fuel with stack filters, and finally, imported power. It's convenient to set up a table for each of the 5 variables to show the method being used to generate energy, the results in terms of pollutants, and the cost per megawatt hour of that source of energy. If you look at the first line for high sulfur fuel, you see it generates 4.5 kilograms per megawatt hour at a cost of $3.50 per megawatt hour. To account for the stack filters, look at the third line for X3. Here we have high sulfur fuel with stack filters. The stack filter reduces the pollutants by 90%. So now we have 0.45 kilograms per megawatt hour, but the cost per megawatt hour of burning this fuel increases by 80 cents. So we go from $3.50 to $4.30. We have a similar shift when we compare low sulfur fuel, X2, with low sulfur fuel with stack filters, X4. We now see that we have 0.5 kilograms per megawatt hour of pollutants, and the cost is $5.80. The data in the third column, the cost per megawatt hour, provides the coefficients for the function that we want to minimize. And so you can see it's 3.5 times X1 plus 5 times X2, and so forth. The final stage of specification is to define the constraints. The first constraint is that we must produce at least 2,000 megawatt hours of electricity, and so we simply add up the amount of electricity generated by each source, and that must be greater than 2,000. Then we have the requirement that the pollutants are less than 900 kilograms per hour, and so we consider that X1, the high sulfur fuel, produces 4.5 kilograms per hour, low sulfur fuel 0.54 kilograms per hour, and so on. And the sum of these terms must be less than or equal to 900 kilograms per hour, which is the EPA specification. Then finally, imported power is limited to less than 200 megawatts. So we have X5 is less than 200. Let's examine the formulation of the electricity blending problem. We start with specifying the library and then the number of constraints and decision variables. So in this case, we initially start with 0 constraints and 5 decision variables, but we will add constraints as we go. I set the pollution level, 900, as a variable because we will examine changes in this pollution limit in subsequent runs. So it's easy to set it up as a parameter rather than have to search through the code to find the value. Then we define the objective function to minimize the cost, the demand constraint that we must have at least 2,000 megawatt hours of electricity produced, the two supply constraints, one on pollution levels and one on input power. Then finally, we solve the model. Once we've executed solve LP model 2, we can extract the minimum cost, the values of each of the decision variables, and the shadow prices. Copy and paste the code from the slides into RStudio and execute it. You should get the results shown on this slide. Let's investigate the situation where the EPA changes the limit to 700 kilograms per hour. This is an easy change because we set up limit as a parameter, so we can now change it from 900 to 700 and rerun the code. Not surprisingly, the cost function increases because now you have to remove more pollutants, and we make greater use of the stacker filters, as you can see when you look at the results for X3 and X4. The transportation problem is another common problem that can be formulated in linear programming terms. In this case, we have 3 warehouses holding paper that has to be shipped to 4 print shops. You can see that there are constraints on the supplies at each of the warehouses and demands for each of the print shops. The company wants to minimize the cost of shipment from warehouses to print shops, at the same time satisfying the various constraints for supply and demand. In this case, there are 12 decision variables, how much to ship from each warehouse to each print shop. Given that there are 3 warehouses and 4 print shops, there are 12 decision variables. And for each of these, we have a cost of shipment from the warehouse to the print shop, as shown in the table on this slide. I've formulated the linear programming problem so that it's easy for you to see how the various components are created. For example, I specify that there are 3 supply constraints and 4 demand constraints. And so in the LP model, I can multiply these 2 variables to indicate the total number of constraints for the model. Similarly, the objective function is set up so you can easily see the relationship between the coefficients in the table on the previous slide and the layout of the objective function. The first supply constraint specifies how much is sent from Detroit to the print shops in Boston, New York, Chicago, and Indianapolis. And this must be less than 250. Notice that all of the coefficients in the first line are 1 and the other 2 lines are 0. The ones indicate that there could be a transshipment from Detroit to Boston, Detroit to New York, Detroit to Chicago, or Detroit to Indianapolis. Similarly, the second constraint is with regard to shipments from Pittsburgh to each of the 4 print shops. Therefore, the first row is all zeros, the second row, which refers to Pittsburgh, is all ones, and then the third row is all zeros. The final supply constraint refers to Buffalo. Now let's look at the demand constraints. In this case, we're interested in the columns. And the first demand constraint indicates the first demand constraint deals with shipments to Boston. And these must be greater than or equal to 75. The second one deals with shipments to New York. So in this case, it's the columns that are set to 1 for the particular print shop of concern. We can solve the linear programming problem, get the objective function, and the values for each of the decision variables. I wrote some additional code to transform the results in a table that make it easy to compare the specification of the problem with the recommended solution. The table at the bottom of the slide shows the results from the linear programming algorithm, and I've also added in the supply constraints and demand constraints so that you see that the answer satisfies all of the constraints. Let's examine the shadow prices. Remember, you ignore the first value from the get Joules solution results. Look at the table on the right side of the slide. For the 3 supply sources, Detroit, Pittsburgh, and Buffalo, Pittsburgh has the lowest shadow price, so increasing capacity at Pittsburgh will reduce the cost by $7. On the demand side, the shadow prices indicate that the best place to increase demand is Chicago. The cost of an additional unit will go up by $12 to supply Chicago. The worst place to increase demand is New York, where the shadow price is $20. Shadow prices are a nice byproduct of the linear programming algorithm, as they help to make decisions, in this case, as to where to increase demand or supply and to minimize total cost in the process. Reduced costs is another output of the dual solution to the linear programming problem. In this case, it helps us to decide where we might increase capacity or demand and what the change in costs would need to be. The upper table shows us the results of applying the linear programming algorithm to determine what to ship from the warehouse to the print shop. In this case, we see that we moved nothing from Detroit to Chicago. The bottom table shows that in order to ship from Detroit to Chicago, we would have to reduce this cost by at least $4. Similarly, we would have to reduce the cost from Detroit to Indianapolis by $3. So the reduced costs indicate what sort of reductions in cost we would need to make in order to make a particular warehouse a viable source of print for a particular print shop. A second optimization problem we will examine is known as the traveling salesperson problem. Every delivery company faces the problem of determining the shortest path to deliver its parcels to every customer. More broadly, you can think of this as finding the shortest path to visit each city in a given list exactly once and then returning to the starting city. This problem is used for vehicle routing, computer wiring, and many other applications. Here's a map showing the shortest path to visit all cities in the contiguous United States with a population of at least 500. This was done in 1998, so we'd have to do a new map now. Here's another example with even more cities, and it gives you some idea of how it might be applied to laying out the wiring for a computer circuit where you want to minimize the cost of wiring. To solve the traveling salesperson problem, the first step is to set up a matrix with the distance between each of the cities to be visited. We set the diagonal to 0 because the distance between a city and itself is 0. To solve the problem exactly, you would have to consider all of the possible permutations among the n cities for traveling between them. But this would be expensive to compute. So typically we'll use some heuristic that gets a very good approximation to the very best solution. In a symmetric matrix, the distance from city A to B is considered as the same as the distance from B to A. If this is not true, then you can set up an asymmetric matrix where the distances vary. In most cases, assuming a symmetric matrix is good enough for a very good approximate solution. We will use Google Maps to get the distance between any pair of cities. Make certain you have a Google API key to access Google Maps so you can solve the traveling salesman problem. Here is the code for setting up a matrix. You'll notice that we need a number of libraries, and that you need to read in your Google key. We're going to do a European tour of Georgia. That is, we're going to visit all of those cities in Georgia that have names corresponding to European cities. The core of the code is a double loop to use Google Distance to compute the distance between two cities in driving mode. The loop is set up so that we compute the distance from A to B, but not B to A, and we assume that we have a symmetric matrix. Copy and paste this code into RStudio and execute it and have a look at the distance matrix. Here's a distance matrix I computed for the 5 cities. Yours might be a little different because Google continually updates its map and maybe changes the algorithm for computing the distance between 2 cities. Once the distance matrix is established, it's fairly easy to solve the problem using solve_TSP. Notice that we set start equal to 1. We want to start at Athens, which is the first city in our list of cities. The shortest tour is 536 miles, and we go from Athens to Dublin to Vienna to Rome and Oxford. The solution looks even better if you can put it on a Google map. And in this case, here is the code to enable you to do that. It shows a straight line between each of the cities, not the exact route that you would take. If you want, you can use the Google Map application to map out exactly the roads that you would take to make the Georgia European tour. Modify the supplied code to do a true European tour. Start in Rome, Italy. If you have a problem that can be defined as a set of linear equations, then you can use linear programming. For example, last year we had a Masters of Business Analytics project where the client wanted to compute the best schedule for his staff given certain skills and other constraints. This is a linear programming problem, and we were able to define a set of equations for him to use in solving this problem. There have been extensions made to the linear programming algorithm to handle the requirement that the solutions be an integer, or you have non-linear constraints or objective functions. The traveling salesman algorithm computes a near optimal solution. It is too expensive to compute all of the possible permutations in a long trip. But there are good algorithms for getting a very close approximation to the very best solution. This year, some MSBA students have a project to help one of the MSBA teams this year is using the traveling salesperson algorithm to solve a delivery problem for a large car dealership in Atlanta that supplies parts to many companies that repairs the cars that it distributes. Optimization tools are very useful for those interested in sustainability because they compute the optimum use of resources. Look for opportunities to use them.